Hello everyone. So I think we can start workshop now. So maybe for the latecomers, then they will just join us later. Yes, I'm Tien from MLDA. Um, yeah, this is my email. So if you want to like contact me or ask me any questions after this, then she'll just drop me an email. Okay. Yeah. So first, I just want to briefly introduce about MLDA at EEE. So MLDA at EEE is an integrated lab profile platform for EEE and IEM students to learn more about different aspects of machine learning, data analytics, and AI. And so also we can also facilitate the connection with many industry partners. So as you can see in the right, we have many projects. We have like we can do FYP, DIP, or Eureka projects under MLDA. We also have many industry projects from our industry partners, so that you can get exposure to the industry. Yeah, and then many other workshops and competitions, like just like the workshop today. Yeah, and in terms of resources, then we have quite a lot of resources, as you can see in the left. Yeah, so we have a lot of GPUs that you can use for the um, machine learning and other like deep learning networks. Yep. So moving on to the actual workshop content. Okay. So for the agenda for today, it's quite brief. So first, I will just like cover some theory of transfer learning. So the main point is just like to get some intuition why we do in transfer learning and how it can benefit you to create a better model. Yeah. And then next, I will touch a little bit on the workflow. So a typical workflow that you can expect when you want to build your a transfer learning model. And then finally, you have some hands-on time so that you can build your own transfer learning model with TensorFlow. Yep. So first, I will start the workshop with a problem. Yeah. So imagine you have a collection of images. Yeah. So maybe you like take a lot of images, and then with this collection of images, right, you want to only view the C photos. Yeah. And then because like you have a lot of images and they are unsorted, it's like very messy. And then you want to automate this because you are like engineering student. Yeah. So of course you cannot like go through all of your collections and actually like sort them out one by one. You want to automate this. Yeah. So this can be also known as like image auto tagging. I think like some like Microsoft or like Facebook also have this kind of features when you upload your photos to their cloud. Yeah. So as you can see in this task, then we can put the machine learning task as the image classification because we want to look at one image and then to see whether there is a C photo or not. And then some constraint we have that you see we actually don't have a data set because it's just your photos, right? And then you want to identify it. So maybe I mean you can manually label a few photos, but you cannot obviously like label everything. Yeah. So as you can see, we have a like a small limited data set, and then we'll see how transfer learning can help us to do this. So for the purpose of the workshop, right, I won't be asking you guys actually like use your photos. So we use this image data set. It's called the Intel image classification. So as you can see here, they have quite a lot of different landscape images. Yep, and then they also have like C photo. Yep. Okay, I will use my cursor. How do I get? Okay. Okay, so you see this one, right? This is like C photos. Yeah, so maybe for the purpose of this workshop, I will use this data set so that later we can try how to train a transfer learning model based on this data set to classify like C images. Yeah. So what is transfer learning actually? Yeah. So the basic idea of transfer learning is that you want to apply some knowledge you learn from one task to another. So for example, you want to train a C classifier, right? You can use something quite similar. For example, like a leg, as you can see here, like leg classifier. And then you hopefully, like some of the things that your model learned from the leg classifier can be applied to your C classifier so that you don't have to waste time and retrain your model again. So in practice, right, actually people don't actually use like those kind of like very direct models like from leg to C. What they actually do is that first they have like something called upstream training. So they will train a model with a very large and general purpose data. So most of the time they will train on this data set called ImageNet. So later I also elaborate more on that. So once they learn, once the model learn about how to classify a very large and general purpose data, right, the model can actually identify many general features. And from these general features, right, you can fine tune the model based on your application. So for example, here you give them like a lot of C images and maybe a lot of like non-C images as your negative samples. And then from this general model, you can like fine tune into your own model for your application. Okay. Yeah. So in today's workshop, we'll focus on image classification, which is like a more easier task to do. So I just want to revisit again like a typical model for a image classification network. So uh, usually the first few layer will be like convolutional layer and the max pooling layer. And then the last few layers will be like fully connected layers, also known as like dense layer. And then of course you have like the output, which is like equal to like the number of classes that you have. So the idea I want you guys to get here is that the first few layer, right, you can understand them as like only extracting the image features. So the reasoning behind like a convolutional layer is that they are very good at extracting, for example, like a vertical. Okay, change my pointer. Okay, for example, they can like identify the edge of the bird here. Yeah, or maybe identify like the round shape of the eyes. Yeah, actually we don't actually know what they are trying to extract, but that's the reasoning behind we using convolutional layer. And then after they are extracting the layers, right, the features, right, they're gonna summarize them inside this dense fully connected layer. So this is like like a vector, and then a vector you have a lot of numbers, right? So each number will represent something we don't know, but it's actually good enough for us to understand how to classify the image. So instead of looking at this like very complicated model, right? I want you guys to look at this, introduce the black box model. So in this black box model, right, you don't really care what your model does. You only like, you know that you put your image inside, the model do something, like the project model do something. And then what you get is that you get a output vector, which is a features vector. So as I said before, right, this feature vector summarize all of the important features that you need to know about the image. You can think of this as like the fingerprint or like the signature of the image. The idea is that like similar images, right, should have like very similar vectors, and they should stay very close to each other inside the vector space. So the idea behind transfer learning is that you can treat this as a black box, right? You just want to obtain the feature vector here. And then for a feature vector, you just add now the classification head, depending on the number of your classes. And then your model will only need to learn from this vector here, how to classify the image. So as you can see, it shows that we don't need to actually train this whole part, right? So it reduces the training time a lot. Yeah. And then, okay, for the next slide. So this is a scatter plot from the previous dataset I show you, the Intel image dataset. So as you can see, there are 6 classes, right? And then it's quite obvious for you to, so actually this one, I visualize the vector space here. So actually the vector space is like very high dimensional, around 1000 or 2000 something. And then I do some dimensionality reduction so that we can plot this in 3D vector space. Yeah, so as you can see, it's quite obvious that like samples from the same same class, right? They stay together like cluster. Yeah. So as you can see, this we have one cluster here, one cluster here. There are some cluster at the back, we can't see it because it's behind. So actually later you can, actually you guys can write the code to plot this also, and you guys can like navigate around and then see how it works in 3D. Yeah, so as you can see, right, because using transfer learning, we imagine you already have this vector space. So what do you need, your model need to do, right, is only learning the boundary, how to like have a boundary between the classes, like in this case, the cluster. So maybe your model can learn like, okay, this is a boundary. So this part will be the, this is street, yeah. And then it will learn the boundary here. So it understand that this part is the forest. Yeah, so this will be like the general intuition while you're using transfer learning, because the pre-trained model is already so good at extracting the features, right? You only need to like, from these features, you understand, okay, so maybe the street, you have like um, somewhere in the vector space, and then you just need to understand where's the decision boundary to get those classification. Okay, so next moving on to the transfer learning workflow. So a very typical transfer learning workflow. First, you need to define your problem. So just now I introduced you the problem, right? You want to identify your C images. So in this case, we already know that in terms of the machine learning, it will be called image classification. Yeah, and then next you need to gather your data. So I mean, in real life, you will want to use like your personal data, but in this case, we just use the Intel image classification dataset as I mentioned in just now. So in the bottom here, right, it will be the bottom here will be whatever you do. And then this part here will be the upstream on the one that you obtain from internet. Yeah. So imagine like some researcher or some like Google or people somehow, they do some like kind of like state-of-the-art models and they train with the ImageNet. After that, they upload it to the internet. So in this case, we're gonna use a pre-trained model from TensorFlow Hub. So it's like a website you can obtain a lot of pre-trained models for TensorFlow. And then you just need to choose an appropriate model from TensorFlow Hub for your application. And then you train the model, and then after that, you can deploy your model for the application. So just want to talk more about the upstream training, right? So I think it's very important to understand what's actually happening at the upstream training, like this part here. So first is about the ImageNet dataset. So ImageNet dataset is a very big dataset contain of a lot of images. So as you see, there are like 14 millions and 20,000 categories. So I don't think you can ever get any dataset as large as this. And then I put a link here. So actually you can go inside this link and then see what photos they have. Yeah, so imagine like once a model has been trained on this image, right? It's like so good at detecting like different kind of objects, and then whatever your application is, right? It will be much simpler than that. So obviously the model project on this will perform very well on your specific application. So I put like a screenshot from the ImageNet website, right? As you can see, there are a lot of classes. So as you can see here, like whatever you can think of, right? They have whatever you don't think of, and they also have. Yeah, and then for each class, they have like a lot of photos. So in the actual website, you can click the photos and see, yeah, quite a lot of interesting photos. Yeah, and then the ImageNet dataset is also used as like a benchmark for like research models. So to understand whether like a model is better than previous models or not. So I take this graph from papers with code here. So as you can see, right, throughout the year, the performance on the ImageNet dataset actually improved. So it's a good thing that we are still improving over the years. Yeah, and then I want to highlight the part that, okay, yes, okay, so if you go online and then go to a lot of tutorials, right, most of them will just use this ResNet for your transfer learning. Yeah, but in today's tutorial, I'm going to show you how we can use the EFficientNet, because as you can see, the EFficientNet is like 2019, right? So imagine like usually like some technology that people do in research usually takes like 5 or 10 years until you can actually use it in like actual business application. But in this case, like you can even use like some state-of-the-art, like very modern research techniques only last year, like 2 days already, and then you don't even need like a lot of resources to use it. Yeah. Okay. So next, okay, so go back to the workflow, right? Go back to the workflow. So choose an appropriate model, right? So actually, this is not also not cover much in like online tutorials about just for learning. So there's this thing called accuracy and throughput trade-off. So imagine, right? Your model can like get very accurate, but it will be very slow because your model is very complex. So depending on your application, maybe you want to prioritize throughput, like the speed. Yeah, because maybe you deploy your model on a mobile phone or like an embedded device. Yeah, but in our case, this doesn't matter to us too much. So we just want to use like a moderately very high accurate and high speed model. The next thing you also need to consider is that the model size. So actually for all of the models, right, there are a lot of variants. So in this case, I'm taking a screenshot of EFficientNet, which is the model that we're gonna use later. So as you can see, right, they have like B0, B0, B1, B2, B3, B4, B5, B6, B7. Yeah, so usually the higher number indicates that the model is bigger and more complex. And then although it's more complex, right? So it means that it can get better accuracy, but sometimes the bigger the model is not better for your case, because as the model gets more complex, right, it requires more training time and also it's very hard to without sufficient data, your model will easily overfit your data. Yeah, so even you can see here, right? Even like for ResNet, you have ResNet 50, ResNet 152. Yeah, so the rule of thumb, that's like the smaller number is in that, the model is smaller. Yeah, so later I think we're gonna use P3 because it's like a moderate accuracy and then moderate amount training time. Okay, so next. So after you obtain your pre-trained model, right, then you need to prepare it. So actually there are only three main steps how to use a pre-trained model. So first you only need to prepare the image input because like the people whoever pre-trained the model, right, they prepare the image input in a certain way and you have to follow the way they prepare the image input. Yeah, so later you're gonna see. So most of the models from TensorFlow Hub, the image will be, they will give you like a dimension. So maybe like 244 times 244. And then what are the range of values on maybe like some kind of transformation they do on the image. And next will be the pre-trained model, right? So this one you just download to your computer. So usually it's just like one line of code in Python. Yeah. So as I explained before, after this black box, you get this feature vector, right? So you just slam on it a classification head. So yep, and then you just like learn this part. Yep. Okay. So and then for the classification head, then the number of output neurons will be equal to the number of classes. Depends on your task. Yeah. So in terms of training the model, basically there are two ways to train the model. First is that you only train the classification layer. So as you can see, right, you can only train the weights um, to apply from the feature vector to the classification layer. So actually this is what I have been saying, that you only need to train this one because the model already create a very extract like very good features that like very distinct for different classes. But actually you can also train the black box inside. So in the second image, right, I already like, it's not a black box anymore. You can see inside they have like a few layers, right? So actually you can, there are two ways to do this also. So you can either train the whole network. So you train like this part, the weights from the feature vector to the classification head, and also train the black box inside. Yeah, whatever layers inside the black box. Yeah, so that's one way. So another way, if you want to do it more selectively, like right, because there are a few layers. The idea is that the first layer usually extract like more basic features like straight line, horizontal line, and then like the deeper the layer is, right, it's like extracting more complex feature. So I don't know, maybe like circle or like some character, I don't know. Yeah, so maybe you want to like just train the last layer only, like maybe the last few layer, like layer C only, and keep the layer A and B fixed. Yeah, so it's for our purpose, then I think we only I'm gonna only cover the first one here, means that training the classification layer, because the second one is more like if you want more performance to your model. Based on my experience, right, usually you just train the classification layer. It's good enough already and very good. You give you very good performance. So that's basically what you need to know about transfer learning. So about the tools we're gonna use later, right? So we're gonna use TensorFlow and Keras. So Keras is a high-level API for TensorFlow. So actually TensorFlow, they have like very low-level and high-level API. The high level is like, it's more user-friendly, easy to use, so you can develop the model faster. So I just like take a screenshot from TensorFlow website. And as you can see here, right, this one is with Keras. So you can see here, I can break down the program. It's like that, only a few lines of code so that you can train the model already. So this one, you create this part, you create the model. This part, you specify the optimizer. And this part, you train the model. And that's all. Yeah, and then as you can see, right, in this one, like small, low-level API, then you have to define the model like in a very complex way. And then when you train the model, it's also not very straightforward for beginners. Yeah, so that's why I would recommend using Keras, because it's very user-friendly to create like, but still a very capable framework. So moving on. Yep, so that's all for the theory part. So now we can move on to the hands-on session. So I understand that the QR code is not very useful, right? Because you're not gonna open the notebook um, on your phone. So I will just copy this link and put inside the chat. Just give me a moment. Okay, so everyone can see the link, right? Just give me a thumbs up when you see the link. Thanks, Daryl. Okay, so we can continue. Okay, share screen. Okay, I'm gonna share my screen again. Okay, so if you go to the link, right, you're gonna see this GitHub repo here. So this is a GitHub repo. So actually, a copy of today's slide is also inside this repo, this transformation workshop.pdf. Hello? Oh, okay, I just continue then. Yeah, so if you want a copy of today's slide, so you can just download it from here. Yeah, so we're gonna using Google Colab, which is like a free online platform that provides GPU for your machine learning training. Yeah, so it's free, so it's very good. Yeah, so follow this screen, right? You just click the open in Colab. So make sure that you use the exercise notebook, which is the one we're gonna use today. Okay. Okay. At this stage, anyone got any difficulties going into this page? So just let me know if I'm going too fast, okay? You can just unmute yourself and say it. You just like do some, is there thumbs down? I'm not sure. Yeah, because like it's a virtual, so it's very hard to gauge whether you guys can follow me or not. Yep. So this is a Google Colab. So I have like right now this notebook for you guys to follow. So actually I explained quite a lot of stuff in the notebook already. So like after today's workshop, you guys can also review and read more about it. Yeah. So first thing, you guys would want to save a copy in Drive. So click File, save a copy in Drive. So that will like save in your Google Drive. Yeah, so later you can review it. Otherwise, if you close this one, right, it will disappear forever. Yeah, it will not be saved. Yeah, so you would want to save a copy in Drive. Okay. So the animals right on top. Okay, so it's optional if you want to have the animals, right? You can go to the tools settings and then miscellaneous. Yeah, you can enable the corgi and kitty mode. Yeah, and then you have like animals. So it's more fun when you train the network, right? So later you can see you have to wait for the model to train. You can look at the animals. Yeah. So just some outline of the notebook, right? So first you're gonna download the data from Kaggle. So Kaggle is like a it's a machine learning computation platform. There's a lot of like open and public data there, so it's very useful for you to like download the data on Kaggle there. Yeah, and then we're gonna choose a pre-trained model, just like the workflow that I showed you guys before. We do some data preparation, like prepare the image according to how the pre-trained model was used. Yeah, we do some training evaluation. We do some tests with your own image, so you can also upload your own image, and you can see uh, how does your model perform. Yeah, and then you can, so I would also go through like what happens with training a very small data set, and I show that transfer learning even with a very small data set, right? It will still perform very well. Yeah, and then I will visualize the feature vectors, which is the scatter plot that you saw in the slide just now. Yeah, so you can play around also. Yep. So first you have to go into this link here to get the data set. So I'm going to open, okay, so I open this in, I have to open this in my, okay, wait. Okay, so I open this in an incognito mode because otherwise I have signed already. So, okay, so for this, so this is the website that hosts the Intel image classification data set. So as you can see here, right, Data Explorer, they already split the data into like training, test, and prediction data set. So in this case, we only concern with the train and test data set. The prediction data set here is for the competition. Yeah, so after you train a model, you do the prediction and you submit the to the competition to see how much you do. Yeah, but it doesn't have label, so that's why we're not concerned with that. So if you navigate the folders, right, you can see The folder structure is quite simple. So if you open the training and test set, right, they have like a folder for every class. So we have like 6 class here: buildings, forest, glacier, mountain, sea, and street. So if you click one of folder, you can see, yep, some of the photos, a lot of beautiful buildings. Yep, and then you can also see the forest. Yep, a lot of forest. Yep, and then it's exactly the same thing in the test set. Yep, you can see more forest photos. Yep. So okay, so basically that's the data set. So normally when you have a data set, right, you should do some kind of like data explore, data analysis, so that you can understand your data set better. But in our case, right, because we don't have enough time, so we're gonna skip that. So so the problem now is that we need to download this image dataset into Google Colab, right? Because there's no point download to your computer. You cannot like put that in your Google Colab anyway. So I need you guys to sign in or register. If you have a Kaggle account already, you can just sign in. Otherwise, you will have to register a new account. So I think everyone have a Google account, so you can register with Google. Yeah. Otherwise, you can register with your email. Yeah. But in this case, because I create already, so I have my own Kaggle account, so I don't need. So maybe I just give you guys some time for you guys to, oops, I close it, to create your Kaggle account. Okay, so I'm gonna open the Kaggle here. So in this case, I have already signed in into my account. Yeah. So um, yeah, maybe you just do a thumbs up like once you have already signed in into Kaggle. So for some of the people just came, right? Um, so there's this, okay, there's a GitHub link here. So just go to the GitHub link, and then you can see the GitHub repo for this today's workshop. So I just need you guys to open the exercise notebook in Google Lab. Just click the button. Yep, and then it will open this one in Google Colab. So you want to like save the notebook in your Google Drive so that you guys can refer to it later. Otherwise, it will be deleted. And then you have to go to Kaggle, this one, and then you have to sign in or create an account if you guys don't have an account. Yeah, so just use your Gmail or something. Yeah, so once you sign in and then you go back to this Intel image classification dataset, right, it will be appear something like this, like my screen. Yeah, so it will be signed in already. So just do a thumbs up once you like on this page, like sign in, and then on the Intel image classification dataset again. So also let me know if you face any difficulties, okay? Yeah, I think I will continue. I give like 2 more minutes. Okay, so I assume that everyone is on this page already. So once you're on this page, right, click to your profile picture. So I think, wait, I think I zoom in a bit so it's easier for you guys to see. Click in the your profile picture, go to your My Account. So and then you guys to go to the, okay, just scroll down, go to the KPI API section. API section here, right? And then you guys can create new API token. So once you click this, right, it will download a file kgo.json. So keep that file. Later we're gonna use it later. Yeah. So I also like write the instruction here. Yep. So generate your kgo token under my account API, create new API token. Yep. So go to your my account, scroll down to the API and create new API token. Okay, so once you have that token, right, and then you guys to upload the file. So okay, in this case, I think I already have the kgo.json file here. Oh, okay, wait, I think I have to restart. Oh, okay, one more thing I forgot to mention, right? You guys should go to the edit notebook settings and then enable the GPU hardware accelerator so that we have access to the GPU. Yeah, because machine learning requires a lot of GPU resource to train the model. So you have to enable that, otherwise it takes forever to train the data. Okay, so okay, so this Google Colab, so it's very similar to the Jupyter Notebook that you guys will be familiar with. So just some like commands to help you to navigate the page, right? So for this one, you can click Shift Enter, so that it will run to the next cell. So it will run this cell here, and then we'll go to the next cell. So it's a very easy shortcut for to remember how to use. Yeah. So first you install the Kgo application on this Google Colab so that you can download the dataset to your Google Colab virtual machine. So next, I need you guys to upload your kgo.json file. So I prepared this file already here. So, but usually when you download, you go to your downloads or whatever. Yeah, so you need to upload your kgo.json. Okay, upload your kgo.json. So once you upload, right, you can see you have the kgo.json file here. And then after that, you run this code. So it will like register the kgo.json file into your system. And once you have the kgo.json file registered, right, then you can download the dataset using the Kgo application. So as you can see here, it start downloading very fast. Yeah, so you can see here, right, the dataset is like 300 megabytes. And then the Google internet is very fast, like 30 megabytes per second. Oh, so if you face that problem, right, it means that you have run the cell bit already. So you can try to run the dataset download command to see whether you can download the dataset. Yeah, so if you guys face any problem, then just stop me anytime. Okay, it works. It's okay already. Yeah. So yeah, this code, the cell here, right? It should only be run once because like if you already register, right, it will throw some error. So just ignore it. Yeah. So after that, you just run this command so that it will unzip the file. So as you can see here, right? After that, it download the Intel image classification.zip. It will be our dataset, and then this command will unzip it. So maybe you need to refresh. Yep. So we have exactly the same data set that we saw on the Kaggle just now, right? We have the train, test, and prediction. So it's exactly the same structure. Yep, for the structure here. Yep. So that's basically how to download Kaggle dataset into Google Colab. So now we can start doing transfer learning. So first, just import the libraries. Yep. who cares about the importing libraries, right? Just import everything. Okay, so next I need you guys to input some code here, but I will walk you guys through it, so don't worry. So first, I need you guys to go to the TensorFlow Hub website. So this website here. So you can open the TensorFlow Hub website in a new tab. So as you can see, right, they have a lot of pre-trained models you can use for your application. So in our case, right, we're gonna look at image problem domains because it will be classification. So you can just look at classification. Okay, so a lot of models here, right? Yeah, and then because okay, we're gonna use a state of the art because that's more exciting, right? So just EfficientNet here. So as you click EfficientNet, right, they already show you a lot of like versions, right? As I explained before, different depend on sizes. Okay, and then there will be okay. Let me look at here. Okay, so for our case, right, I will recommend you to use a B3 model. You can try other models later, but beware that like the bigger the model is, right, the training time will be like much slower. So I'm going to use B3. I click B3. So as you can see right here, right, generally on like the image classification models on TensorFlow Hub, right, there are two versions. The first version will be the classification. So for classification, this one will be they already have the classification head, and then they will classify your image into like the categories of the ImageNet dataset. So you don't want that. You only want the feature vector because the feature vector it's like how you can do transfer learning, right? So if you want the feature vector version, okay, let me try to navigate around. Okay. Actually, look at here. Yeah, this one instead. So we want to use the feature vector version, not the classification models, because classification is the one that output already the which class it belongs to inside the ImageNet dataset. So we only want the feature vectors. So I will use B3. So make sure that you are on this page, EfficientNet B3 feature vector. So TensorFlow Hub also provides like sufficient information for you to understand what is this. So they link you up to the original paper. They also show you how they train it. So you see they train this using the dataset, ImageNet, yep, the one I mentioned, and then they use auto augment reprocessing. Oh, so the feature, okay, so maybe I go back to the slide. I need to share the slide again, right? Wait, okay. You can see my slide, right? So for the feature vector, right? The output you get from the pre-trained model will be this feature vector, like the summary from the features of the image. For the classification version, right? It will be already the classification head, which is like the output of the ImageNet. So for example, if you see, wait, is the ImageNet slide? So this one, right? So ImageNet, here you see you have 20,000 classes, right? So the output of the classification version will be the like out of like 20,000 classes. Yeah. So it will output like whether this photo is categories in the ImageNet, but maybe like whether it's okay. Let's see. Maybe it will output whether it's a cave or not. Maybe whether it's a what's this mouth or not. Yeah. So it will be output the label depending on the ImageNet dataset. So we only want the feature vector because the feature vector it's how we do transfer learning. If you already get like the output, right, you cannot do anything about it. But if you get the feature vector, right, you can like add your own classification head, and then you can train the feature vector, like how to understand from the feature vector, then what will be the class that you are interested in. So does that answer your question? Is it clear? Okay, great. So I will share go back to the TensorFlow Hub. Okay, so yep. So we were at the training, right? So they also say how they train the model. So this one just like for your information, you don't really need to care. And then in this case, they also provide you how to use this model, which I actually adapt from this code. So it's quite also very easy to follow. So you also like can explore all the models here on the TensorFlow Hub. They also provide you like instructions. So that's very good. Yeah. So the more important part, right, will be how they prepare the image input. So in this case, you can see, right, although they never say it like very big, but and you see they for the image input, you should have a dimension of 300 times 300 pixels. And then the input image is expected to have a color values from 0 to 1. Yeah, so normally the image, we have the values from 0 to 255, because that will be 8-bit images. So before you do this for this particular model, right, then you have to transform them to 0 to 1. Yeah, so I think all the models, they also provide instruction like how to prepare it correctly. Yeah, so two things we need to remember here, which is the correct dimension, 300 times 300. And the next one will be the values range from 0 to 1. So you guys just need to copy the URL here. You can just also copy here, copy the link. Go back to the exercise notebook. And then, oh, thanks, Zaro. So so your code here, right? You can replace the code with the URL. Yeah, remember to put the string so that so that you become a string. Otherwise, yeah, it's a code, so it won't run. Yep. So just run this cell, shift enter. So just wait a bit because it's actually downloading the model from TensorFlow Hub. So like after this workshop, right, you guys can also like try to change this link into site another model, so you can experiment with it also. Yep. So after this, you can see the hub model will be this object here. Yep. So next, as I mentioned before, right, we need to build the model. So first we need the correct dimension. So that will be 300 times 300. So width and height will be 300, 300. And then to build the model, you need the classification head, right? Which depends on the number of classes you need. So in this case, so if I open this one again, right? Okay, I don't need to tell everyone. I hope everyone can count. So that will be 6. So we have 6 classes in total. Okay, and then next you need to create, so you use this sequential class. So the sequential is like a sandwich. So you just like put one layer by layer. So the first layer you want is the hub. So the hub, yeah, is the pre-trained model you get, right? And name it hub model because it's from TensorFlow Hub. And then you only need to add the classification layer. So the classification layer will be TensorFlow Keras layers .danes. So you want 6, right? So number of classes, you want 6 neurons correspond to the number of classes. And then you will put activation equal to softmax. Yeah, so these are pretty basic neural networks. So I hope everyone understand this part. So just let me know if you are not following this part. Yep. So see here, right? TensorFlow Keras makes it very easy to understand. So Keras, layers, dense, yeah, number of neurons, and what will be the activation function. And then you run this. Okay, so yay, so we can see the summary, right? You see here, the first layer is the pre-trained model. The next layer is the dense layer, which is the classification layer. Yep, and then you can also see, then, okay, you can see here, right? The total parameter is quite a lot, around 10 million. Oh yeah, 10 million. But actually you're only training, because you're only training the classification layer. So you're only training around 9,000 parameters. Yeah, so that's make like less work for us. So hopefully that will make the training much faster. So you have finished preparing the model. Next, you need to prepare the data. So so for the data, right, you see here, you have this like folder structure. Like you have like a separate folder for each class, and then inside a class there are a lot of images. Yep. So first you only need to put the train path and test path here. So in our particular case, right, you see here they have like nested folder. I have no idea why they're like this, but like just have to follow. So the train path, right, will be sec train over sec train. Okay, and then test path will be sec test over sec test. Okay, so we already set up the test and train path. Next, we're gonna use this function from Keras, image dataset from directory. Yeah. So you can read up more about it here. So you can open this a new tab. So the documentation is quite good. You can actually like read it. Yeah, there are a lot of like arguments and parameters, but the four most important one I want to highlight here. Yep, I wrote here. So you only need to care about the directory, the batch size, the image size, and the shuffle. So I will fill with you guys here. Just follow me. So first is the directory, right? So directory. So because it's a trained data set, so I will put the directory will be the train path. Okay. Next will be the batch size. So if you're familiar with neural networks, right? Because we cannot fit the whole data set inside the GPU memory. So that's why we have to divide the data set into batches so that we can load the data set inside the GPU memory one batch at a time. So the rule of thumb here is that like the larger the batch size, right? It means that you are utilizing your GPU better. So it means that the training speed will be faster also. But then if the batch size is too large, right? Then you cannot fit inside the GPU memory, and then the program will have error to you. So in this case, right, I will put 128. Yeah. So the batch size must be a power of 2 because it's some GPU memory stuff. You don't need to really know. Just remember how to do that. Yep. So I think last time I tried, then 128 still works. Yep. So just put 128. And then I can put batch size, go to batch size here. Next will be image size. So image size, right? We already defined the image dimension above. Yep. So it's very convenient that if you define as a variable above, you can just reuse it. So that will be image dimension. Okay. And last one will be the shuffle. So as you know, right, for the training set, you want shuffle the data set so that every time we go through the data set, it will be like different order. Yeah. So actually, it's better for training. And then for the test set, right, basically you can use the same parameters. Just need to change the directory into the test path. And then you can shuffle your test data set, but actually I recommend not to. Yep, because just make life easier for us. So after you run this command, right, hopefully it works. Yep, it works. So it already print it. So the first one is from the train data set. You found there are 14,000 images belong to 6 classes. Yep, so that's exactly what we can see here. And then this one from the test set, so that we have around 3,000 images for the test set. So after this, right, you can also extract the classes from the train dataset object here. Yep, so you can see it's exactly what you see on the folders buildings for us. Yep, and so on. Yep, so it's very convenient. So next, right, we have to perform some transformation on the dataset because yep, the image that the TensorFlow Hub wants, right? It will be from 0 to 1, as I mentioned before. So we need to do that transformation. I already wrote the code for you. So in this part, you only need to understand the TensorFlow dataset API. So like the train dataset is the above we got, right? It's a special TensorFlow dataset API object. So actually it's in a TensorFlow, this is a computational graph, so that it only builds like what are the operations you're gonna do with this. So once you run this command, right, it actually doesn't import your data inside the program yet. It just, okay, I know this file exists. So later, if you ask me to run, right, then I will actually import the data. Yeah, so it's only a computational graph. And then you can add more operations to that graph. So in this case, I use the map function. So it's very similar to the map that you know in Python or like pandas. Yeah, so the map will just like apply the same function on every object or image inside this dataset. So first I apply the normalize. So in this case, I just divide by 2 by 5, right? So I convert from 0 to 5 to 0 to 1. Yep, so that's just normalized. And then next, I map augmentation. Yeah, so augmentation is actually a very important aspect of transfer learning, or actually for image classification in general, because neural networks quite easily overfit the data. So you need augmentation to like prevent overfitting, and also like generate more data when you don't have a lot of images. Yeah. So the code here I already provide for you, so you can read on your own later if you want to find out more. Okay, so that's done. So we can visualize the photos here. So I use some matplotlib to visualize the images. Take some time. Okay, yay, so we have the images here. So as you can see here, I have the correct label. So for example, label 4 will stand for 0, 1, 2, 3, 4. It's a C, right? Yeah, so I think it's a part or something. Yep, so you can see your images here. So if you run this command again, right? So as you can see here I'm using the train dataset. So it means that every time I go through this dataset, right, the image will be different. So just wait a few minutes. Yep, and you can see they are different. So because we are shuffling the training set. So if I change to the test set, right? Okay, wait a few more seconds. Yep. So okay, this is a test set. So if I rerun this again, right, it will be exactly the same because we are not shuffling the data set. Yep, they are exactly the same. Yeah, and as you can see, their own buildings, right? Because like the buildings are like the first images in the folder, so that's why they'll follow that order. Yep. So I also include some like advanced topic if you want to read more about image augmentation, but I will not cover it like in today's workshop. So that's basically you have finished preparing your model and preparing your data, and next you just need to train the model. So first, in TensorFlow, you need to compile the model. You need to specify the loss. So the loss basically is the measure of how bad your model is. And then the optimizer, it's a mathematical way how to reduce the loss. Yeah. So there are many types of optimizer. I put a very interesting visualization here. So um, the most popular optimizer are S3D, stands for stochastic gradient descent. So this is like the more traditional one. It's like very long time ago already, but it still is very good and used a lot in like image classification tasks. And then the next two popular ones will be ADAM and RNS-prop. So they are adaptive learning rate optimizer. So as you can see, they are learning like much faster, right? So the red one is S3D, so very slow. But meanwhile, where's the RMS prop is the black, right? You see black go very fast. And then, okay, this one don't have the item. Okay, but okay. Yeah, but you get the idea. Yeah, so from my personal experience, right? Actually, S3D give like a better result in the long run. So if you have a lot of time, right, you can use S3D and then you will convert to a very good minimum. But for ADAM and RMS prop, right, although they're much faster, right, they usually will not convert to a local, like convert to the worst minimum compared to S3D. Yeah, but if you don't have a lot of time, right, just use ADAM or RMS prop. The performance they give is quite good already, especially for transfer learning, because you are actually not training from scratch. Yep, so I give, okay, so there's a links here. So you can go inside the links and read more about different types of optimizer and losses. So, oh wait. Hello, hello, can you guys still hear me? Oh, okay, great. Okay, so like this link here to see like different type of optimizer and losses, but to save time for our purpose, right, I'm just gonna type the answer here. So for the optimizer, right, you can either use ADAM or S3D, doesn't matter. In this case, I'm gonna use ADAM. Okay. And then for the loss, the one we're gonna use here is span categorical cross entropy.
Yep. And then for the metrics here, I'm using the default ones to be accuracy. Guys can add other metrics if you want. So I compile the model. So this, once I get this stage, we are good to go for training. So to train the model, right, we just need to use model.fit. So very simple. So first, just provide the training data set. Epoch to be the number of like how many times you go through the data set here. Last time I remember it takes quite a lot of time. So maybe for our purpose here, we are gonna put 5. And then validation data set, right? And we're gonna put the test data set. So you press Shift Enter, and then it starts training. So for the first epoch, right, because it's like firing up the data set in the model, right? So it will take like a bit more time. But once you go through the first round of like first epoch, right, it will be much faster later. Okay, so I hope everyone is on the same page. We all get this. Okay, it's here. It start training already. Yep. So the training will take some time. So if you guys have any question, can ask me while we look at this training process. As you see here, right, we only start training, just like start training a few seconds, and the accuracy already reached like 65, 66%. Yeah, which is quite impressive. Consider like the model haven't like actually trained on our data set yet. Yep. So imagine if you like train the model from scratch, right? It will start, I don't know, like the first few will be like 0 or 2, 5% accuracy. Yep. Yeah, so there's really like no reason why you shouldn't use transfer learning if you do like some very typical machine learning tasks like image classification. For the optimizer, you said Adams may only actually in like machine learning, right? It's hard to say that there is like a global minima. Yeah. So I don't. Yeah. So usually like there's really like usually it will just converge to a local minima. It's like we don't even know whether like a local minima exists or not. So yeah, and then like usually in like just for learning, you have a lot of parameters, right? So the space that you're looking at, it's actually like very high dimensional. Yeah, so it's hard to say if there is an actual global minima. So yep, so Adam usually because it's go faster, right? So I think you can read more on this, like some articles, but they say like because it go faster, so it doesn't maybe it skips some parts. Yeah, it skips some time because it's too like eager to go. Okay, you see here, it's too eager to go to the go down, right? So maybe it missed out. Maybe like there's something somewhere else. I'm not sure. Yeah, somewhere else that maybe SGD can go somewhere better. Yeah. Yeah. So also like one more thing, right? One interesting thing is that you can also like go to the like in this case we can go to their original paper, right? Like actually we can also see how they train their model. So they always like publish their parameters to train the model. So okay, just wait for a bit. You can see what type of optimizer they use also. So I'm just gonna Control F and say optimizer. Yeah, so you can see here, in this case, they are using RAS prop with like decay, momentum, and whatever. So yeah, so actually this also like maybe a good suggestion. So you can also go into the original paper, see how they train. So maybe you can copy their parameters also. Okay, let's see how it goes. Okay, we just finished the first epoch. Okay, you see here, right? Just like go through only like one time over the data set, right? You already get a validation accuracy 90%. Yeah, so that's like very good already. Actually, you can stop here already. Yeah, don't need to do much work. Okay, so I think maybe for the interest of time, I just for the interest of time, right? I think I will just wait after the second epoch, and then I'm gonna stop the training. Yep. So in your own time, you can also like uh actually like after you put the machine to train, right? You just like go out do something else. Yeah. Why my one is only 69%? Um, we run differently. Um, yeah, actually, because like the pre-trained model, right? If you use the same pre-trained model as me and then follow my all of the code I wrote here, right? It should give roughly the same. But I want because when we initialize, okay, if I go up, right, I go up to my model here. Where's this? Okay, when I build a model here, right, I add like this classification layer, right? So when I create this, it will like initialize the weights with some random weights. So because it's random weights, right? So my initial weights will be different from yours. So that's why the performance will be a bit different. Yeah, but I don't think it should then be that much different if you are using the same model as me. So that one I'm not very sure. Oh, okay. So one more interesting thing here, right? As you can see here, the accuracy is around 85%, but the validation accuracy is 90%, which might not make sense, right? Actually, it also like to me for the first time I see this also doesn't quite make sense because like usually the validation of the test accuracy will be smaller than the training accuracy, right? Because they are the data that you haven't seen on, but you are performing better, which like not very logical. Yeah, but I think like after like searching online, right, reading about it, right, I think like one reason to explain this is that um the neural network in the training mode, right, behave a bit differently inside the testing mode. So in the training mode, they have like some regularization techniques like batch normalization. Okay, so I'm gonna stop here. Okay, so it's around 91%. Yeah, so because those batch normalization, right, it's like they are do some complicated math or maybe even like drop out so they forget some of the weights. So because of that, right, they are like more conservative during their training process, but then during the validation or during the testing uh, mode, right, then they will not like try to apply regularization on the weights, so in this case it will perform a bit better. So actually you we only observe this when you're doing transfer learning. Yeah, I think if you train from scratch, you won't be able to observe this. Yeah, so just some observation if you guys think that is weird. Yep. So after this, you can visualize your data, but because I stopped this before we finish, right? So if I run this, it will not do anything. Yeah. So if you guys have time, you can rerun this one, wait for it to finish, and then you can actually visualize the training process. So actually, I can go to the solution notebook, right, which is the one with like everything, just to show the graph. You can visualize the training process here. Yep, so you can visualize training process here. So see the loss going down and the accuracy going up. Okay. So there are also like other advanced topics about training because from my opinion, right, training a neural network, it's like an art more than a science because you don't really know like what parameters to choose and how to train the a neural network to get the best local minima. Yeah, so there are a lot of techniques about this. So I can kind of leave it here so you guys can read more about this after the workshop. So next you can evaluate the model, right? So just use the predict. So it's very straightforward. So in this case, I'm gonna build a confusion matrix so we can understand like how our model performs across the classes. Okay, take some time. Is there more ways to speed up training? Yeah, so actually, I think I was about to mention this point. Is that for okay, so one thing that people actually don't mention, right? Like in this case, like for demonstration purpose, I use EfficientNet, which is like a state-of-the-art model. But a lot of people never discuss that like they always like publish, okay, this model can achieve like this accuracy, it's very good, but they never discuss how easy it is to do transfer learning on the model. So like some of the models you see online, right, some models are easier to do transfer learning, like you can do the learning faster, you can convert to your specific minima faster. Some models are not. So in this case, right, maybe I just like introduce here, because since you asked, like TensorFlow Hub, right, they have this bit, okay, bit M. Yeah, they have their bit model. So the bit model is like a custom version of ResNet that Google did some changes to the ResNet. It was created specifically for transfer learning. So yeah, so maybe you want to use this one instead if you actually want to do transfer learning for your application. Because from my personal experience also, right, this one trained much faster and converge faster also. Yeah, and then if like, but if you still want to use EfficientNet, right, because the accuracy will show the potential, how much your, like how good your model can reach there, right? But like whether it's easy to get there or not, like they normally don't discuss. But if you still want to use that model, there are some techniques such as let me remember, half precision training. So like on the weights of the model, right? There are some data types like float 22 or float 16. Yeah, like double precision or single precision. But then like on the modern GPUs, right? They have like the tensor cores. So if you guys are familiar with like the GPUs, then they have like this tensor cores to do like uh, this kind of like matrix multiplication, the tensor multiplication, yeah, basically to speed up training. But the tensor cores only works for half precision, which is like a bit float. Yeah, so you might need to like change the weight, the data type into a bit float so that you can utilize the tensor cores in the GPU. Yeah, but this one is like very advanced. So, but like personally, I don't know how to do that also. Yeah, so some techniques I know. And let me think if there are any other techniques to speed up training. Increase the batch size, which I already told you. And then uh, um, I mean, you can also use a better GPU. That's not a very good advice, right? It's more like how with our resource, we can speed up the training. So I think I can't think of anything else at the moment. So if I think like, if I can think of anything else, we'll just tell you later. Okay, so move on. So this one, I'm just gonna get the labels from the dataset. Okay, and then I get the label from the probability. Okay, great. So we have the uh, confusion matrix. So for those who don't know, right, confusion matrix plotting our true labels against the predictions. So what we want is that we want the diagonal line to be the brightest, because it means what? This one, it means that you are predicting buildings and they are actually buildings. This one, it means that you are predicting forests and they are actually forests. So if you look at this cell here, right, one here, right, it means that you are predicting forests, but they are actually glacier. Yeah. So whatever is not on a diagonal line, right, it means bad. Yeah. So from this one, it's quite interesting to analyze this confusion matrix. So for example, you can see here the data point that not on the diagonal line, right? it will be the brighter one will be 58 and 91 here. That will be the glacier and the mountain. So one way to understand this is that actually the glacier and the mountain are quite similar, right? There's some kind of like the mountain structure. Yeah, so it's understandable that why our model get more confused between these two classes compared to others. And then you also like street and buildings, right? So imagine if you have a photo of a street, right? There will be buildings along the side of the street also. So maybe that's also one reason why our model confused between the building and the street. Yeah. So this just like some reality check to check understand why our model performing in this certain behavior. Yeah. So okay. So next you can test with your own images. So you can upload your image here inside Google Colab. So ideally, right, you want to test an image that like inside one of these categories, because if you try to upload like I don't know, an image of a cat, like it's not that something that your model have been trained on, right? It will be something called out of distribution image. So because if it's out of distribution, you get some unexpected behavior. Yeah. So I mean you can try, it will be quite interesting, but don't expect any like meaningful result from that. So I also have I prepare my a sample image from me. Okay, so this is an image I took some time ago. So you just need to replace the name of the image to the test image here. So just wait for your image to upload. So as you can see, right, like my image is around 3 or 4 megabytes, and also already took quite some time to upload to Google Colab. So imagine if you try to upload like 300 megabytes of dataset into Google Colab, that will take forever. Yeah, so that's why it's a better idea to download your image using the Google, using the Kaggle app inside Google Colab. So I finished uploading. So I plot my image here. You can see, right? So this is my image I took a few times ago. So you see there are a lot of buildings. Yep. So hopefully, our model will predict this image to be buildings. Yep. So I also need to prepare my image like the same way I prepared the dataset. So yep, just walk through. So I need to divide by 255, right? So convert from the normal 8 bits to 1 to 2 range. And then I need to resize the image, and then I add the batch dimension because our model expect a batch, it doesn't expect a single image. And then, yep, I can see the shape is correct now. So the first dimension, the first number in the shape will be the batch size, yeah, which is 1 because we have a single image. It will be the dimension. And then the last one is the number of channels. So we have red, green, blue. So that's why 3 channels. Okay, so we can do prediction. Okay, so okay, building. So great. I look at the class with the highest probability, right? Buildings. So great, our model works. Yep, you can try your own other images. So I just do this. I make it a data frame so it looks nicer. So it's in here. The buildings is the highest probability, right? But you can see street also has a very high probability. So maybe because like, I mean, there's a street here, I guess. It's not that obvious. Yeah, but then street and buildings are quite similar. So that's why our model can have like kind of high probability for street here. Yep. Okay, so next one I want to show you guys that we're gonna try to train our model on a very small data set. So in this case, I'm gonna take a small sample of the Intel image classification dataset. I will take only 100 training images, which is around 17 images per class. So this one I already fill in everything. So just need to like shift enter to go to the next cell so that can run. Yeah, so in this case, I use the ResNet, but feel free to use other model. It doesn't quite matter. So because our training set is only 100 image now, right? I can afford to have like 10 epochs because each epoch is very fast. Yep, it just blazing through. Okay, so after 10 epochs training on a very small data set, right, we get a training accuracy of around 84%. It's not that good, but I guess it's pretty impressive because imagine you only have like 100 images and then you keep training, but you still already get 84%. Yep. Um, in this case, I can visualize the training process, yeah, because it was quite fast. Next one will be more interesting. So I'm gonna evaluate our model on the test set. So remember this model, right? It's only trained on 100 images, which is very small. And now I wanna evaluate this model on the test set, which have 3,000 images. Yeah, and then this one I only trained for 10 epochs, which is very short amount of time. I can easily increase this to like 20, 100, yeah, 200 epochs. And then you see what the accuracy we're getting. We're getting 74% already. So just wait for it to finish. Yep, so we got 76%. So even with like a very small image training set, only 100 images, we already get so good results. So that also like the reason why we should do transfer learning. So even with a very limited data set, we already get a very good model. So in this case, I'm gonna plot the confusion matrix again, but with the new model trained with the smaller data set. So it will take some time also. Okay, so as we expect, right, the classes that our model kind of confused, right? It's still kind of the same classes. So it's still places and mountains. It's in here, right? Confused quite a lot. It's also confused quite a lot between the buildings and the street. Yeah. So this is because we only have 100 images. So that's why like there's only around 17 images per class, right? So for each class, like our model doesn't have enough samples to like generalize each of the class. So that's why they got quite confused a lot here. But in general, it still performs quite well. Yeah, which is pretty impressive. Yeah, imagine if you training from scratch, right? This kind of like impossible to get this kind of accuracy with only 100 images. So, okay, in this case, I'm gonna predict this on the same photo again, the same photo I put here, my own photo, but with our new model here. So this will be a very interesting behavior, right? So as you can see here, so actually the class that have a highest probability is the street now. Yep. So as I said before, because our model doesn't have enough of like image to generalize, right? So it's still confused a bit between the buildings and the street. Yeah, but then the street and buildings are quite similar. So that's also quite understandable. And then you can see here, they have a C. The C probability is quite high also. So if you look at my image again, right? So actually, this part here is actually the river. Yeah, so maybe because of the river, it identified that as a C. I don't know. Maybe. Yeah, so but it's interesting to see how our model interpret with just like very limited training data. So that's basically concludes what I want to show you in this workshop. So the next part is just like how to visualize the feature vectors. Yeah, so just run through the few cells. So we will generate the plot. So while waiting for the plot, right, I'm just gonna show you in the solution book because it's already have the plot really. Okay, wait. Okay, it should be loading. Okay, okay, it's loading, right? So this one is an interactive plot, so you can move around and you can see, right? It's very interesting, right? So each of the class is like they belong to like one cluster. And then one interesting thing you can also see from here is that like the class that you see previously, they're confused, right? They're actually like on this plot, they are also very close to each other, like they are blending in. So the green and the purple, right? They are mountain and glacier. So our model previously like have troubles uh, differentiating them, right? Because like as you see inside the vector space, they are kind of like blending in together. They are not that much distinct. Yeah. So that's why our models have been troubles understanding this. So remember this plot, right? This plot, I'm just getting the feature vectors from the pre-trained model. I haven't trained anything yet. So this is like whatever I get from the pre-trained model. So as you can see here, also understand why, like what is like the potential we can, how much we can get from a pre-trained model to like understand each of these clusters. Yeah. So quite interesting, can move around. And then this one here, right, is I put the test image, the same test image I show you guys. So as you can see, it just like from looking at this graph, right, I don't even need a sophisticated machine learning model. I already see that this test image is like belong to the purple. It's not very obvious, but yeah, even I don't need machine learning model, I can see my test image belong to the purple cluster. So that would be the buildings. So that's actually how our model interpret the data and learn the decision boundary inside the dataset. Yep, so I also include some read-ups. So if you want, like, because this just, okay, go back to the, oh, haven't finished running. Okay, okay, so just wait for it then, yeah. So this is just like in the notebook, right? So if you want actually use this model in whatever application or your personal project, right, then you need to deploy this somehow. So first thing is that you need to save the weights. So to save the weights, you can connect to Google Drive. So in Google Collaborate, you can click this button, Mount Drive, and then you can save the weights inside directly in your Google Drive. And then from Google Drive, right, you can download your weights, and you can just keep it there also. Yeah, so it's very convenient. You can also like load your weights from the Google Drive, and then you can use directly from there. In terms of deployment, right, there are many options. So because the TensorFlow ecosystem is very like huge, so they have everything that you need. So if you want to deploy your TensorFlow model on like a web server, right, you can use TensorFlow serving. You can read more about that here. If you want to deploy your model on like a browser, you can use TensorFlow.js. If you want to deploy your model on like mobile phone or like embedded devices, then you can use TensorFlow Lite. So TensorFlow have everything for your needs. Yep. So that's kind of what I have to, okay, so this finished running already. So I guess from your side, it's also finished running. So we can play around with the graph. So go back to the slide, right? Actually, I have a few more slides to show you guys. Actually, only one more slide. Okay, I just go to the, okay. Okay, so what I cover is the image classification, right? Which is a very like basic task. Like usually it's like the easiest task in like deep learning. So if you are more interested in like using just learning for like NLP tasks, right? You can use that also, and just for learning is actually like one of the reasons why some of our modern models is so good. So most of the just for learning models for NLP, they actually train on the Wikipedia data. So imagine that would be like the largest text data you will ever get. So they just train the Wikipedia data. So some of like NLP stuff is like word embeddings. So word embedding is basically a vector representation of words. So the the words having similar meanings, right, will be stay closer to each other. So you guys can click into this to like see some visualization. So okay, so I take a screenshot here so you can see like increases and reduces, right? They are like opposite meaning. So they should be like kind of close to each other. And then enable. So all of these words are kind of like have similar meanings. Yeah. So this is actually very useful in NLP tasks because it gives like a understanding of the words, and then helps our model to convert from like the words to like some numbers to do some math calculations. So, and then next will be like some language models, right? So everyone knows like the latest news about GPT-3 by OpenAI. It can basically do everything. yeah, anything. Yeah. So actually, what they did, so they train on the internet data. I think also Wikipedia, like even more Wikipedia. So the idea is that since they train on so large data, right, it kind of understand the human language. So that's why it can do basically everything. Yeah. So like when you use like BERT or GPT-3, right, actually kind of you are doing transfer learning because you're using the knowledge they learn from the internet to your specific application. Yeah. So the idea is actually kind of similar to what I showed you guys just now, but then like how to use this kind of models, right? Actually like more complicated. There are more steps. So one library you guys can get this kind of language models from will be Hugging Face because they make like preparing the inputs and the outputs much easier for you guys. Yeah. So you guys can discover that if you guys into like NLP machine learning. Yep. So I think that would be the end of the workshop. So this is a QR code for feedback form. So just scan the QR code and give your honest feedback to me. Yep. So I'm just gonna leave this for a while. So if you guys have any questions about like transfer learning or about a notebook, can just ask me now. What if we have own collected? What could be the best way upload it? Okay, so if you have own image dataset, right, the best way will be upload to your Google Drive, and then you mount your Google Drive to Google Colab, and then you can. Okay, so okay, I can show you. Okay, I have to share my screen again. Okay, so in this case, I can mount Drive, right? So I connect to my Google Drive. Okay, I have to run this. Okay, I'm gonna stop sharing, so I connect first, and then I show you guys later. So basically, you need to sign in, right? So that you authorize it, authorize Google Colab to access your Google Drive. Okay, share screen again. Okay, I mounted add content drive. So you can see here, where is it? Okay, refresh. Then, okay, you have Drive here. So basically, my Drive. So it will be basically your Google Drive. So you can access everything here. Yeah. So this is my like my school stuff. Yep. So you can with this, right? Because it's content.drive, right? You can just, for example, okay, no collab notebooks. You can just copy path. Yeah, and then once you copy path, right, you can just okay code. You just paste the path here. So this is like where you load your image dataset, for example. Okay, chat. What other application can be used with transfer learning? So transfer learning is just a technique for you to like save time and effort to build a model. So the application will be depends on your problem. Yeah. So and it also depends on like the models because it's just a techniques for you to make the like the process of creating the models much easier and faster. So I mean, if you look at this notebook overview again, right? I mean, I include a lot of text to the explanation, but actually there are just like a few lines of code to get the model running. So I have like the importing datasets. I create the model from TensorFlow Hub. So only a few lines of code also. Oh, can you give example of use case? So I mean, one example. Okay, I share the my PowerPoint. Okay, because like for the purpose of the workshop, I just do image classification, which is easier, right? So like one example I give in the beginning is that image auto tagging. So you can do this to like auto tag image, like you have the collection of image, right? You can just like manually label a few image. You train the neural network, and then you use the neural network run through the rest of the image, and it will be automatically like categorized the rest. Yeah. And then for some like NLP use case, so like one common task in NLP is that it's sentiment analysis. So you look at like online forums, right? And then you see whether this is like a positive or negative sentiment. Yeah. So in this case, we want to use like some like pre-trained word embeddings or like some language model like BERT, for example. You just use that, you pass through and then understand the sentiment of like the online forums. Yeah, so I mean, what you use with that information later, it's up to your application. So maybe like you want to monitor what's the sentiment of the online forum during like COVID, different period of COVID. Yeah, you can see how the internet react to the COVID events. Yeah. Okay, so going back just one. Okay, yeah, so you can see here, right? Just a few lines of code, you create a model. Basically, you just put this and then you import your data set. Yeah, do some, looks scary, right? But it's just like very basic stuff. Yeah, and then you just compile the model and then you feed the model. So that's all, just a few steps and you already get very good results, 90% accuracy. Yep. So if you have nothing else to ask, you can leave the workshop. Thank you for your time. I know it's a Friday evening. Yeah, you can could have done like something else, but you decided to join my workshop. So I really appreciate you for that. So hope to see you guys more in the future. So I put my email here. So if you have like any more questions or want to discuss stuff with me, you can just like drop me an email. How is the fine tuning able to improve the model so much? Isn't the pre-trained model is already? So actually, it's not like uh, so far on Grace's question, right? Because okay, let me go back to the slide. Maybe wait, let me which one? Okay, maybe this one. So so in the pre-train, right? What actually they do, right, is that for the classification head. Okay, I use a marker. The pen. Okay, for the classification head, right? They use their own classification head. So that will be the ImageNet categories. So they have like what to 20,000 output neurons for the classification head. Yeah. So actually the weights you're training, right? You're training these weights, the part in the middle. So when you do like transfer learning, right? You don't look at this. You don't look at this the classification head from the ImageNet because you don't want that's not your the output you want one. So you remove this. So basically you remove this part also, the weights that you the model was trained on, like from the feature vector to the classification head. So you remove this, right? So okay, I clear that first. Point the erase on in here. Okay. And then so imagine first you only so the pre-trained model is only this part. And then oh whoops. And then you add your own classification layer. So this one you add this one. So it means that the weights here, right? This part here, it will be first initially randomized. And then what you're training, right, is that you are learning this part only. Yeah, look, you're not learning the whole thing. You're only learning this part. So that's why at first it's quite bad because actually it's like it doesn't know which neurons from this, right? Which neuron will be associated with like C or forest. It doesn't know that yet. So that's why the performance is quite bad. But just like a few iterations, right? Because the feature beta is it's good. So it's like I show you the vector space visualization, right? There's a very clear distinction between the classes. So it knows, like for example, okay, maybe like a C photo, we have these neurons, so it will activate this, go to the C classes, and maybe like a car, maybe like a mountain, it will not like this value will be quite small, so it will not activate the car. So that's why we're just learning this part, the weights here between the feature vector and the classification head, and then so that's why it's bad at first. Yeah, like in when you do training, it's always bad at first because it's randomized one. Yeah, so because but basically the feature vector is good, so that's why you can learn the process very fast. Yeah. So I hope that I answered your question. Oh boy. Okay. So I'm gonna just leave the feedback form here. Okay, so this is the feature vector, just pre-processing data. It's pre-processing data. Um, I mean, if you say pre-processing data, I mean, from certain standpoint, you can say that because it's kind of like we extracting the features from the image. And then we don't really care how this process was done. But whenever we say like pre-processed data, right, it usually means like some rule-based, some like you do, you pattern the image, you reduce the dimension to this, you resize to this, or you enlarge the image to this. Maybe yeah, you divide the image values to like 0 to 1. So usually people will say that like pre-process the data, but this one, I couldn't call it pre-processed data. Yeah, but just like extracting the features. Yep. Here is some. Okay, so I answered that question first about transfer link before, and sometimes they could say like freeze the laser. Okay, so the freezing laser, right? It's actually I briefly mentioned about it. So when so in this case, you're not like when you want to train more stuff, right? Like in front, usually yeah. So for example, if I recall the earlier layers are like they're extracting the basics basic features, right? Like straight lines, horizontal lines, something like that. So you want to freeze this layer. So freeze. Okay, very hard to spell with my touchpad. Okay, yeah, you want to freeze this, and then you are unfreezing this. So that's why you are training like the nearer layer to the output. So that's why they say unfreeze. So you want training the weights at the later stage of the layers. Yeah, and then in this case, right, the one that I show you in the workshop here, right, because I want you guys to think this as a black box. So, but it's actually not a black box, right? They are actually layers, right? So what actually happens is that what I did is that I freeze everything here. Yeah, so you guys are not training anything before the feature vector. Yeah, so that's what they mean. So Andrew asked me, okay, yeah, Andrew asked me that his confusion matrix is a bit messed up even though model has been trained. So I mean, this really depends on the model choice and how you train it. So wait, let me exit this. Okay, stop sharing. So discard, okay, I'll share again, this one. So I think like I tried to run this notebook quite a few times, and then from my personal experience, right? Usually it will be quite good like this. Actually, this one like are the better ones already. Yeah, but maybe you use a different model from mine, so maybe that's why. Yeah, so that's why I'm not really sure. Yeah, but yeah, usually because the training of the neural networks, they are not like deterministic. Every time you train, it's a bit. Every time you because we initialize different random weights, so that's why every time we train, it's not exactly the same. Yeah, but if like you train more epochs, right, it should like converge to the similar minima. Yeah, maybe because in this case we only like train for like yeah, I trained for only 2 epochs. Yeah, so maybe that's why a lot of difference. Okay, if you guys don't have any more questions, you guys can leave the workshop. Mm. Oh, do I have more chance? Do you know like when we should like freeze the entire pre-train or unfreeze? I think there's like no scientific way to do this. Like in the past, right? I tried to like first I freeze the whole pre-trained model, and then I unfreeze the last few layers, and I continue training. And then the performance actually is worse than if I just unfreeze everything from the start. Yeah, but actually, it will be that actually depends a lot on your dataset, your model, and a lot of factors. Yeah. So again, it's just like trial and error. So there's no clear rules how to do this. Yeah. Oh, so one thing I forgot, right? Like for publicity purpose, right? I will take a screenshot of you guys so you guys can turn on your camera and show your beautiful faces. So I can forward to my publicity team later. Yeah, it's sad that I forgot that, so we didn't get the chance to see everyone. So you guys can just turn on your camera now. Wow, when I ask turn on camera and then you guys start leaving, I'm very sad. So that I ask you guys to leave and then never leave. Okay, never mind. I just gonna take photo of whatever we have. So 1, 2, 3. Okay, thank you. I got a screenshot.
Tian, maybe I just share. I think yeah. Can you try to find out the problem? I don't know why, like because like the
Oh,
convolution matrix that
sure, you can share your screen. I make you co-host first. Okay, you can share your screen.
yeah. So like my convolution matrix is a
Oh,
bit
oh yeah,
really
that's really bad. Okay, can you go up? Maybe it's
yeah, the loss is already
wait, this
low.
okay, go. Wait, the confusion matrix is it for the full data set, right? Oh, okay. Wait,
Yeah.
okay, I see the model.compile.
This one.
Oh, okay. You go up to the top and when you the sequential when you create the model. That's very strange. It's exactly the same, right?
Yeah, and yeah, I use the same model, the efficient B3.
Oh, it's the feature one, right?
Sorry?
You scroll up, can I see the link? Is that the feature Victor? It's that's very strange.
Or maybe because the data set is shuffled, I don't know. Like, so like when you, the label and the prediction is different.
Label. But it cannot be that much different from mine, right? So that's why I find it very strange.
Shuffle the test data.
Like the accuracy is already quite good, like 92%. 92. Yeah.
You didn't change anything about the confusion metrics, right? That's very strange. I have no idea why.
Okay.
This.
You shuffle the test
No,
data.
I have no
Like
idea.
it's shuffled.
You shuffle the test data.
Where?
The shuffle is true.
Oh, you shuffle
Oh.
test data.
Oh, you shouldn't shuffle.
Oh.
Okay.
Yeah, you shouldn't shuffle.
Oh, I see.
Yeah,
Yeah.
here.
Because actually, like, for the purpose, yeah.
The
No,
one should.
test is below. Test should
Yeah,
be false.
Yeah, test is false. Yeah.
Oh, I see.
The train is true.
Okay. That's why. So need to train again, is it? Or
Yeah, but
no
then
need?
train. Oh, no need.
Just
Only need to run the
directly.
confusion matrix again.
Okay.
Yeah.
And no need model.compile also, right?
Yeah, because it's the same model. You're not changing anything.
Oh yeah. Okay.
Okay.
Much
Yep.
better. Okay.
Yep.
Yep. Thank you, Tian. Thank you,
Okay.
Yong Hao.
Yes. Thanks.